Oh, red. And
98 degrees. Seeing and measuring our observations. Whether sunlight exciting electrons to emit red, or a thermometer stealing heat from my mouth, there's always interaction that influences the objects we observe. We call it the observer effect. We can observe the moon, me, and cheese to have definite position. I'm right here, so graph me as a point. However, tiny particles have what's called superposition, which is like hide and seek. They can be found in a range of hiding spots, but must stay within the boundaries. We describe this with the Schrödinger equation as the boundary for where they can hide, and they're more likely to be under the bigger areas because there's more spots to hide in. So what influence does the observer effect have on quantum waves? If a photon came into contact with an electron in superposition, its wave function collapses to a particle residing in one point in space. This alternating behavior of waves and particles we call wave-particle duality. So take a seat, because we're about to see the effects of wave-particle duality at a macroscopic scale. Introducing the double slit experiment, a wall with two thin slits that we shoot electrons through and record the pattern it creates on the other side. The wild thing about this experiment is that it completely changes if we look away. If we observe the electrons with a detector as they come out, the observation collapses the waves to particles, and the electrons then travel directly to the back wall, like a particle would, resulting in two long lines. Now, another trial, but this time we remove the observer, turn off the lights, and let the experiment run unwitnessed. What? An interference pattern? But this could only mean waves. Without observation, the electrons remain in superposition, so an electron would pass through both slits at the same time, interfering with its own crests and troughs. And once it collides with the back wall, the electron has constructed a high probability of collapsing in the center with lower chances on the peripheral, and a zero probability of being found where the waves deconstructively met. We see these results after the fact when the lights are back on. Quantum physics shows the beauty of observation. A close friendship between particles and waves, teaching us that the observable universe is really only half the story.